This film shows how corrosion damage arising during service can be greatly reduced by optimizing corrosion control at the product design stage. For example, in the 1970s, when this film was made, the useful life of vehicles was limited by bodywork corrosion. Now this problem has been essentially solved by attention to key details during vehicle design. The film was developed for the European Federation of Corrosion. Although it dates from a different era, the messages in the film are as relevant today as they were then.
Almost any structure, even a large and expensive one, can be at risk from corrosion. When these expansion joints were designed, not enough consideration was given to drainage. And even in summer, surface water will still be contaminated with salts, used to prevent the formation of winter ice. There is always a need to protect against likely corrosion, and often the extra cost at the design stage would be small. A simple cover would have greatly reduced maintenance. Cars are attacked by water and road salts, and most rust out before they wear out. More complete protection could be provided, but at additional cost. And most people who buy a new car sell it before corrosion becomes their problem. Conversely, because failure can lead to catastrophe, in the design of aircraft, much more attention has been given to avoiding corrosion. Exterior shape can also prevent corrosion. When lifted well off ground, the underside is accessible for maintenance and painting. Good design of legs eliminates trapped water in crevices and facilitates cleaning. Inside, an outlet pipe at the bottom and machined flush gives the essential complete drainage. Designers are familiar with the stress-raising property of notches. But in a corrosive environment, at a stress at which it would normally be safe, a material can fail. For example, a section from a high-pressure pipe suspected of being liable to stress corrosion cracking was tested. A sharp notch was cut into it, and then a fine crack induced. The end of the crack is marked with a scored line. Put in tension, the opening of the crack is measured with a transducer. In a non-corrosive atmosphere, the crack opens slightly as the load is applied, but does not grow any further. When the corrosive is introduced, the crack starts to grow. Eventually, assisted by corrosion, the specimen breaks under a load it had previously withstood. When two plates are bolted together, they form crevices. If one of the plates is metal, in a moist environment, lack of dissolved oxygen in the crevice with higher oxygen outside sets up an electrochemical cell, producing acids. There is crevice corrosion. If the plates are totally immersed in a mildly corrosive medium, the conditions inside the crevice are again different from those outside. And again, crevice corrosion will occur. The attack on outside surfaces is negligible. The designer can avoid crevice corrosion by preventing the penetration of moisture. This can be done by complete sealing, with mastics, coatings, or by welding. Seawater is very aggressive to metals. It will even attack stainless steels, especially if a crevice is formed. This is a problem in pumps, where in idle periods the stagnant conditions may allow crevices to corrode. Can be overcome either by flushing with fresh water before shutdown, or by using different materials. Metals which corrode slowly will often be protected by the corrosion products left on their surface. So that if a liquid is moving slowly, there will be an acceptably low rate of corrosion. But rapid flow or turbulence may remove the protective layer and permit severe corrosion. This is termed erosion corrosion. It can occur in any situation which increases liquid flow sufficiently. In a seawater pipe, as a valve closed, the rush of water increased and removed the protective oxide layers. Erosion corrosion occurred. The remedy for the designer is to use either a larger valve or a more corrosion-resistant material. In industry, erosion corrosion causes many problems in cooling water systems, and most can be overcome by design. With many heat exchangers, where seawater is used as a coolant, in spite of filters, inlet pipes are seen at maintenance to be partially blocked with debris. This can affect flow and give turbulence, which, in turn, can increase erosion corrosion. We have seen that when metals are placed in an electrolyte, such as seawater or wet earth, each of them may corrode. However, when the two dissimilar metals are brought into direct contact with each other and immersed in an electrolyte, the corrosion of the steel will be accelerated. But at the same time, the copper will have been protected. This reaction is turned to advantage in cathodic protection, used, for example, on underground pipes and ships. On its own, the steel hull would corrode in seawater where paint had been damaged. So, zinc blocks are fitted in good electrical contact with the steel. The steel is protected, and the zinc corrodes. With zinc blocks fitted in the right places, the hull remains intact as long as the zinc is replaced regularly. In an electrolyte, metals have an order in which, in electrical contact, they will become either the anode or cathode to each other. This is the electrochemical series. It also includes certain non-metals, such as carbon. When in contact with copper, a metal higher in the series, iron, is corroded. Similarly, when iron is in contact with aluminium, lower in the series, the iron is protected and the aluminium corrodes. In choosing associated metals, the designer must be aware that an incorrect choice can lead to destructive corrosion. Aluminium was chosen to give a light yet strong bridge without the need for painting. But the aluminium girders were fastened by steel rivets. This proved to be an incorrect decision. For where moisture collects, bimetallic corrosion is destroying the bridge. So strengthening has been needed. Bolts of a compatible material, or plated bolts, should have been chosen. In all industry, some 60% of failures which occur from corrosion are due to errors in design. The designer should bear in mind the effect upon corrosion of shape, the need to avoid crevices which lead to corrosion, the flow of liquids, and corrosion by erosion. And bimetallic corrosion from incompatible metals. When all these factors are considered in relation to the economics, the lifespan and the practical use, then there can be prevention of corrosion. Prevention of corrosion at the drawing board by good design.